minus 1.548 and 0.3 sorry, can't remember, 0.631. Yep, this is our turning point here, and the other turning point will be positive 0.2 something 215 and the y value is minus 2.11. Okay. Okay, this is for question B, the nature of the turning point. So let's analyze each turning point separately. Okay, let's analyze the first turning point now. So the way to the way to prove or show, okay, in exam, if they use the word prove or show, you have to do the question in the following way. Okay, so we write down the differential equation, which is 3x squared plus 4x minus 1. Okay. So and now we draw a table. Okay, so when x is equals to minus 1.54, okay, the dy dx is 0, means there is a stationary point. Okay, and I label it like this as horizontal straight line. Okay, and when x is less, okay, the correct math simple is minus 1.54 minus, we put a minus on the top right hand side. Okay, this means when x is just less, when x is a little bit less than minus 1.4, okay, this is that it means, and the dy dx, okay, we can substitute it into the equation. What I do is I will find the gradient is positive. The gradient is positive, and I will have this shape. Similarly, when x is a little bit greater than 1 minus 1.54, the gradient is less than 0. Okay, so I will have this shape. Because of that, so at x equals to minus 1.54, okay, there is a maximum, okay, there is a local maximum turning point. Okay, this is how we prove or how we show there's a maximum turning point at here. Okay, and this is basically the nature of the turning points. Now let's do the same thing to the second turning points. Okay, so we do the same thing to the second turning points. When x equals to 0.215, the dy dx, the gradient is 0, means there is a stationary horizontal line. Okay. Also, when x is a little bit less than 0.215, okay, the gradient will be will be a minus number. Yep. So it will be a minus number there. When the gradient is a little bit greater than 0.215, okay, the gradient is positive. So it would have this shape. Okay. From here, I can say I have a minimum local. Sorry, I would have a local minimum turning point. Okay. Okay. Thus, at x equals to 0.215, okay, there is a local minimum turning point. Okay, this is how we do this question. Okay, when they ask you to show or prove the nature of the turning points. Okay. Also, in some cases, okay. Also, in some cases, like this, if I have an equation y equals to x cube, okay, and when I differentiate, I would have 3x cube, and when I make the differentiate function equal to 0, I hope to find a turning point, and x is 0. Okay. If we do the same thing for this turning point here, okay, let's do the same thing. So if x equals to 0, dy dx is going to be 0, so I will have a horizontal line there. And when x is 0 minus, okay, a little bit less than 0, my gradient will be positive. Okay, so, let me dy dx will be still greater than 0. Well, I would have this shape. Okay. When x is a little bit greater than 0, the gradient is positive. And I label the shape like this. Okay, so from the proof, I don't say a local maximum or local minimum. Actually, I don't even say a turning point. Okay, so what's happened is, okay, at x equal to 0, there is a point of inflection. Okay, and if we draw the graph would look like that. This is y equals to x cubed. X belongs to R. Okay, so okay, this is the proof of the point of inflection. So at this point, this is the point of inflection. Okay. Okay. And yep. So again, in exam, if they ask you to show or prove the nature of a turning point or the nature of a stationary point, you have to do this kind of thing there. Okay, you have to do this. You have to write. Actually, you have to write down those stuff like that in order to get a full mark. Okay.